circuit breaker, which was invented by Thomas Edison about 150 years ago. What's on the side of this building, on the side of your house, or whatever is basically that same circuit breaker. If I just compared to a normal electromechanical device to our chip, it's a kind of 90% plus size reduction. Well, our little 10 amp chip, and we start brainstorming, wait a second, this is perfect because 10 amp chips is 100 amps, and 10 of those is 1,000 amps, and 10 of those is 10,000 amps. And we won the award for semiconductor innovation for AI. Every quarter we have an all-hands meeting. I tell everybody in the all-hands meeting, 5 to 10 years, everybody you know will be touched by some application that the Ideal Switch is in.
Hey, Russ, thanks for joining us here on Micro Journeys. Exciting to have you on here. We've been not only colleagues, but longtime friends. So this is great to have you on here for this episode. So
no, I appreciate it. This is I'm looking forward to this. Will be fun.
You have quite a journey here that I want to go ahead and cover. I mean, starting back in your time over at New Mexico, I know we've talked a lot about it. You went to University of New Mexico, correct?
Yeah, I went to the University of New Mexico in Albuquerque. I grew up most of my life in Albuquerque. My family's from New Mexico, and so I went to University of New Mexico. Graduated in '82, a long time ago.
Yeah. Well, I mean, was it a double E focus that you were in?
So double E focus, engineering and technology is kind of in my blood. My dad graduated from the University of New Mexico, was an engineer, contractor for Sandia Laboratories. He worked at the test site in Nevada. So we were back and forth from Nevada to Albuquerque a couple of times. My uncle, Philip Castillo, he got his doctorate at the University of New Mexico. He was a chief at Air Force Weapons Lab, now a research lab in Albuquerque for years and years and years. My several cousins in engineering. So a lot of us went to the University of New Mexico. Couple went down to New Mexico State, the rivals, but a lot of engineering in the blood.
Yeah, it's well, I mean, and having that kind of a background, I mean, it really allows you to appreciate kind of what you're getting into, right? It's not something that is really foreign. You get to see, how all this hard work ultimately turns into things that are utilized by a variety of different industries, right? So after you finished up in New Mexico, what was your first job after you did that? I think you said something.
So my first job was at Hughes Aircraft. I think at that time they were the largest employer in California. This nonprofit aerospace company, which kind of was a training ground. I guess the number of people that I've run into or crossed paths with after all of that time, all these years later, that worked for Hughes Aircraft in California was amazing. So I was in the Hispanic Engineering Association, and they had some really cool internship opportunities. And so while I was going to after the first year, I started interning out at Hughes for actually three and a half years. And so got a lot of experience, met a lot of cool engineers then. And then I took one different job. I did take a whole semester off, and I got a job, not through my uncle, but I got a job working at in a laser lab at the Air Force Weapons Lab. And worked for a guy named Dr. Vern Schlee. And that was a real intriguing episode of both my education and early career here. I worked in this lab with, I don't know, I guess there was half a dozen PhDs, and what we were doing was they were designing and experimenting pulse laser for Star Wars laser. You remember back in the day, back in Reagan's period, and so
why don't you describe Star Wars? I mean, because most people will think of Luke Skywalker coming out with his lightsaber and
so basically it was a laser system to be able to have defense capability in space, right? And so I think the Reagan administration came up with the term Star Wars because it's like these lasers firing and knocking other satellites out of the sky and stuff like that. Well, what we were making was what was called an alignment laser to align that kind of a system. I was probably too dumb to really even realize all the different implications of this, but I had my own lab and my own light table. And what the engineering team would do was have me set up experiments. So I was kind of acted like a technician, like an optics technician. And so I'd lay out this light table with splitters and combiners and different things for the light. And then what we actually made our own tubes there. And so I think it was some different iodine compounds, and what we would do was they'd build these tubes. They actually built the lenses on the tubes, and excite the material and see what lased at what powers we could get out of it. It was really pretty. It was one of the most fun jobs I ever had, and it really solidified my desire to kind of get out there and learn new things and new materials and try to bring new products to bear.
So this is one of the lasers, like you said, it's an alignment piece that is helping to just coordinate with some of the other satellites that are there, just kind of keeping everything, in a connected fashion out in orbit. Is that kind of the idea?
I believe that was the idea, but like I said, that the scope of that part of it was kind of beyond my need to know, I guess, is probably the right way to put it. But it was more understanding, how to work with materials, experimentation, methodologies, and those kinds of things. That was, for a pre-bachelor degree engineering student, it was well beyond any kind of experience it could normally expect. And when you had a boss, so like I said, Dr. Vern Schlee, and I remember him telling me, he said, go get your degree, keep your grades good. He said, and make sure you just learn Ohm's law. I'll teach you everything else you need to know.
Well, I mean, most kids, when they're going through school, right, they get, go fill up the cup of coffee or hey, go staple some stuff. I mean, you're actually in here in a lab doing some, testing stuff that will impact some kind of program. Yeah. Like you said, there's probably multiple layers here, but you're in there and you're actually, learning what it's like to fail, learning what it's like to succeed, and having a mentor that's able to, craft the set of experiments that you're doing and the such.
And now he wanted me to come there after I graduated. I ultimately went to Hughes Aircraft in California. I think it was partly the lure of sunny Southern California. Ended up staying there. I've been here till then, or since that time. So.
Okay. So over at Hughes, I mean, what were you doing over at Hughes?
So at Hughes, I worked at Hughes for about 3 years. The biggest piece of that, it was all in radar and communication systems, and we were testing the end radio products, if you will. We worked on a couple of programs, TPQ 36 and 37. Some people listening might be old enough to know those programs, but it was called Firefinder. This was a system that could detect fire, pinpoint it, and fire back to that precise location. And so that was a pretty neat program. That's where I really started falling in love with RF, millimeter wave, radio kinds of products. We also worked on another product called and people would freak out if they saw this stuff today, right? Since it's almost 40 years ago, but it was called PLARS, Position Location something system. I can't remember exactly what the acronym was.
Yeah, we'll put it in the show notes. We'll look it up.
It was a man-pack. It was a man-pack radio, but it was all position and location, right? So used radar triangulation as well as some early satellite constellation. It had no voice communication, but it was this gigantic pack on your radio. So fast forward, or on your back. So fast forward 20 years after that, and I was running a little startup company called UNAV, micro navigation, but UNAV, and we made a single chip device, 5 millimeter on a side, that could do all your GPS in a small little package. And now, guess what?
It's in
It's
everything.
embedded. It's in everything. It's in your car. It's in your phone. It's in your watch. By the way, we did have the first watch with GPS in it too. Sunto was the company. We didn't have fancy user interface, and so only people that are sailing on ships really care about longitude and latitude. And so I don't know how much you know about Sunto watches, but Sunto's been a world's kind of leader in naval navigation kinds of sport watches.
So this right here is kind of your first experience in miniaturizing a technology that is usable by multiple people, right? So being able to triangulate where you are instead of having these humongous backpacks, trucking them around and the such. Now, I mean, it's at the micron size or even smaller, and in all of our day-to-day lives. So that was kind of like the initial, piece of, hey, I have a way of, turning this into not only something smaller, but the utility can go through the roof for just mankind in general, right?
Oh yeah, everything for GPS, and now the combination of GPS and RFID. You can track everything,
100%.
right? To a pinpoint location, which is so it's inventory, people,
and the industry.
I think if I look at my phone here, my wife knows that I'm sitting in this conference room because of what's it called, 360 or whatever.
and when you pull money out of the bank, I mean that runs off of GPS. Right. I mean, there's so many of these different. It's integrated in our day-to-day lives, and you don't even think about it anymore, right?
Yeah, and so if you think about this, so 2000, so that's only 25 years ago. So anyway, that's one's always a fun one for me when I think about this first Polaris Manpack radio and how advanced we become, where it's even from a defense standpoint, it's in munitions, it's everywhere.
Yeah, so I mean, and it's interesting you mentioned the defense point. I'm sure that we're going to touch on defense-related items, a number of different times here. I mean, that's kind of how we met, right? You have a pretty long and distinguished career, so I'm going to just kind of poke around one of the items that we had overlap on, not personally, but with our set of connections and the such, is your time over at Microsemi. Yeah. So you started over there at Microsemi. Give me a little background on what that looked like.
What I probably need to do is back up a little bit even to Silicon Systems and TI days. So there was a group of mentors at Silicon Systems, which was really my first big, I'll call it, career move, and it was a company that I think when I joined it in mid '80s, it was a $10 million company. By the time I left, it had been purchased by TI and was doing, I don't know, somewhere between $800 million or so in revenue. So it was a really fun ride. But that team, so it was a group of people. Gentleman named Carm Santoro, who's no longer with us. He was a semiconductor industry icon. Rick Gerner, Jim Peterson, many people know him as Jimmy P, yep. Who ultimately ended up being the CEO of Microsemi, and he was building that company. I was working a couple of startups. I mentioned the UNAV and there was another MEM startup we can talk about later called Weispry. Jim kept saying, "Hey, come over. We got something big going on here. We're going to really build a company that's going to mean something." And Jim's quite the visionary. So I finally moved over, but it was because of those early days of working with him and some of that team at Silicon Systems. Shifted my career from just the product and technology side into really understanding other aspects of building a business. As you probably are aware, Microsemi was on a terror of acquisitions for a number of years.
Yeah, they're the example for a great semiconductor company that did the buy and build model, right? I mean, they just continue to do acquisition after acquisition. You see, these layers associated with the company continue to expand, which created the entity of Microsemi, right?
Yep. So here's kind of a cool story. And I remember saying, Jim, I don't want to go work for a diode company. Come on, and no, we got bigger things than that. So finally joined. 2 weeks later, Jim and another colleague of mine that's actually on our board here, Steve Litchfield, he's the chief strategy officer at Max Linear right now. They sat me down and said, "Okay, now we're going to tell you why we brought you here. You're an IC product guy. We're buying Actel."
That's a huge
buying Actel. I said, "Well, don't we have? Aren't we a diode component transistor company? What we're going to buy an FPGA company?" And he laid out the strategy here, and it was ingenious, because the military business or aerospace defense business for Microsemi was a huge piece of that, and being able to build specialty products and space products and all that. Actel was really the leader in aerospace and defense, especially space, for FPGAs.
FPGAs, field programmable gate arrays.
Yeah, exactly. As you can imagine, FPGAs are particularly suited for defense, because you really don't create the characterization of the product until you're in the field, right? So they're all kind of generic as they're running through a fab, and when and I know you guys looked at this back in your DMEA days. Is how do you do the security? Well, now you're securing a software program that's going to program this FPGA to be whatever chip it needs to be. Anyway. Bottom line is that here we had 0% product overlap, and I don't know, it was something like 60 or 80% customer overlap, right? And so you're selling all of these products into the same. So now you start looking at how to, what systems do they go in together?
So you're just cross-selling.
It was a huge cross-selling thing, and it had a large amplification aspect to it, and continued to grow the business like that. So I worked for Microsemi for 5 years. I got to run 3 companies. So it was Actel, Zarlink, and then Symmetricom. All had pretty large crossovers into both commercial and DoD or aerospace and defense kinds of applications. It was a cool job, right? Because we'd acquire somebody. I got to run the company for whatever 9 months to a year and a half, and then integrate it back into Microsemi, and then go and do the next one.
So this buy and build model here is really taking Microsemi, the diode company, and turning it into a one-stop shop for electronics.
One-stop shop. And of course, our messaging back then was really driving it to be an integrated circuit company, because as you know, the value differences was, especially back then, was pretty big. And so Jim and the team did a real good job of continuing to grow that.
Well, and one of the things that I'm thinking of here is change is always a very scary thing, and it takes a number of bold people to think, hey, okay, this is actually doable, because there's a trajectory, right? Here's our mission statement of company Microsemi, and we're building out diodes. That's what we're going to do. And lo and behold, I'm going to pick you up, Russ, and I'm going to have you help lead the charge for FPGAs. I mean, that is a humongous, not only risk, leap of faith, whatever you want to call it, right? I mean, it's just a different way of thinking about this. And the industry was not really doing that quite regularly.
No, and as a matter of fact, even post that, I won't name names, but I've had several discussions with other CEOs or leaders on acquisition strategy. And well, we see what you did over there, but or what the Microsemi team did over there, but I don't really agree with that strategy. Well, I cannot agree with it. One is it worked, and two is how many companies where, okay, we've got to have technical strategic alignment. What does that really mean? Is failed because the first premise of the Microsemi methodology, if you will, was fiscal accretiveness. If you have accretion right out of the chute, your probability of success goes way up, right? Because now you're not buying something that's a drag, and if something's too aligned with what you already do, and it's accretive, it doesn't necessarily. It's not. You don't get the 1 + 1 = 3 factor. You might get 1 + 1 = 2.1.
Yeah, but now you have a lot of fluff, a lot of fat that you got to cut, right? Because if you buy something that's just already there, you're okay. Do we really need to keep all these excess people? How much IP did we really do? Does it overlap with what we have? So it starts, bringing in a question of, okay, how much do we really need of what we just bought versus we need this to continue.
Well, and that's a great that's a great observation, because that was another learning piece here, because I could either go through those experiences and become known as the hatchet guy or the integrator, and there's a big difference, right? Because the fact of the matter is any of these things, any of these kinds of acquisitions, there's a certain amount of redundancy, right? It's just a fact. The interesting piece to that is if the redundancy is not in the core of the engineering team and the product teams, the redundancy is more in management and overhead functions. The ability to preserve some of the cultures and integrate that culture into the core larger entity culture goes way up. And what ends up happening is if you're able to make fairly rapid decisions on, okay, let's shed this product and this capability because it's not going anywhere. Let's go ahead and double down on these things that are looking successful. Typically, the technical team is aligned with that because it's stuff they've wanted to do for a long time, anyways. So there was a lot of organizational design, culture integration that came from that. The other thing that came from that is that Microsemi had a lot of specialty fabs. People forget about specialty fabs, and we'll talk about that here a little bit, but in our overall ecosystem, it gets forgotten because it's smaller. It's not as sexy as doing a 2 nanometer, lithography.
It doesn't get the same buzz.
It doesn't have the same buzz, but there's an awful lot of things that operate on those things that are built, and sometimes still 6-inch or even a couple of 4-inch fabs around that have some products that are required to make things.
Well, let us not forget. I mean, Department of Commerce came out with a study that showed that these specialty fabs was the foundation of the United States. It was actually one of the evaluations that happened during the CHIPS initiative. Although it didn't seem like they really followed that template too much, which is
I don't know how many of my opinions you want on that, but I think that's true. And as a matter of fact, if you look at, of course, innovation for high-speed transistors and billion transistor high-performance computing and all that stuff, that's all about lithography, and it's all about this drive to nanometer. But and there's tons of innovation in it. Don't get me wrong, but the amount of innovation that's happening in specialty fabs for energy, for communications, for a lot of different fundamental infrastructures that we have can't be forgotten, because those things aren't going to be solved because you have 1 or 2 nanometer lithography capability.
I'd say it's a kind of a two-part piece, right? There's a technology seduction. People are looking to see how they can break the laws of physics and continue to do that. But the second thing is that many of these large companies that are out there that do these kinds of state-of-the-art fabs, mostly in the logic space, have very heavy marketing campaigns to help influence those. I mean, yeah. How many of us know the Intel, jingle that plays, right, when Intel's inside? So, I mean, it's something that people resonate, those two pieces, when they think about semiconductors and fabrication. But, the specialty fab piece is a great springboard into what you're doing today, right? So right now, as the CEO of Menlo Micro, it's focusing in on a very innovative technology that is revolutionizing a core piece that the United States really hasn't touched in quite some time. So would love to hear a little bit more about just Menlo as a whole and how, the technology you guys are doing right here is different than the way people think of, some of the historic technologies.
Okay, so to do that, I'm going to have to tell you a little bit of a few stories, right? So a little bit of history is kind of important here. And usually people say, "Well, you're in Southern California and you have you have a R&D center in New York. Where's Menlo come from?" Well, first of all, Menlo comes from the origins of this whole idea, which is GE. This technology was invented in GE. The material science for it was invented in GE, and it was invented to reinvent the circuit breaker. Circuit breaker, which was invented by Thomas Edison. And
the simple circuit breaker that, just on and off.
Yep. And by Thomas, it's about 150 years ago. And by the way, what's on the side of this building, on the side of your house or whatever, is basically that same circuit breaker that he invented. It looks a little cooler and probably actuates a little bit faster, but it's basically the same thing. And so GE was looking, I left out one part. So Thomas Edison founded GE in Menlo Park, New Jersey. Not Menlo Park, California, but Menlo Park, New Jersey. And so that's actually where the origin of that. And the team that invented this was in Schenectady, New York. GE research. So this fundamental idea was reinventing the circuit breaker. When they started looking at what are the different things we can do for energy and power, and GE had two complementary parallel paths, and I'd say complementary on purpose. One was silicon carbide, and the other was MEMS. And
MEMS.
So microelectromechanical systems. We like to call it microelectromechanical switches, but it is systems is the official name for MEMS. And so what we make, what we make is on the banner back here, and basically they're large by semiconductor standards. There's these 50 micron metal actuators that have metal contacts, and we open and close them. You can put many of these things in parallel or in series. And so all the way back to Dr. Vern Schlee, you learn Ohm's law, I'll teach you everything else. This is basically Ohm's law, at least from an electrical standpoint. From a mechanical standpoint, it's some fairly simple but detailed physics, right? So if I take a bunch of contacts and put them in parallel with each other, by Ohm's law, what do I get? I get smaller and smaller and smaller contact resistance, or a more efficient optimum transfer of energy, right? If I make a contact or an actuator that is 50 microns versus one that's millimeters in size, what do I get from a physics standpoint? I get a much faster actuation that takes far less energy to do. And so instead of a big coil-driven large actuator, I have a little tiny electrostatically driven switch. I can put hundreds of them in parallel, and I get a very large current density by doing that. And so Ohm's law is I transfer energy more efficiently. I create less waste heat, and in a little tiny chip. Okay, and that's the fundamentals behind what we make. Now they were doing a silicon carbide line in parallel because yes, we're orders of magnitude faster than the classic circuit breaker that's on the side of your house, or relay that you might use in an electronic system, electromechanical relay that you might use in any other electronic system. But we're also a physical contact. So there's wear.
So when you talk about, you have the classic way that hasn't really been changed by what Edison invented and where Menlo is today. Are we talking about like a 5x size difference, a 20x size difference? How much is the difference in size here that you're doing, or I guess, yeah.
It's very application dependent because we are in everything from beamformers for satellite communication to we actually are in a contract to build a 10 megawatt micronuclear reactor advanced circuit breaker system, right? Starting with a little 10 amp device. And so the size of the application, the impact of the size of the application varies. If I just compared to a normal electromechanical device to our chip, it's a kind of 90% plus size reduction. If I put it into a large system like a 10 megawatt microgrid, somewhere 5 times plus smaller in size and lighter in weight.
So what I just got from you there is that now size, weight, and power is has a lot more flexibility with a Menlo Micro switch than it would with the classical one.
Huge, right? Because if I don't create heat, I shouldn't say I don't create any heat, but if I create far less heat, then my thermal design is much simpler. My cost is much lower, but more importantly, I don't have big boat anchor heat sinks all over these boards and systems that are expensive. They use up space and weight. So now I end up with, now you start thinking about what does the future mean for something like that. Okay, it's great. If you want to build a microgrid for an aircraft carrier or a submarine or whatever, fantastic. We know that needs to be smaller. Why do I need it smaller for a data center? Why do we need it smaller for an industrial factory? Well, that space is real estate. That space is reliability because waste heat causes reliability issues. And then you start even thinking about grid deployment. This goes all the way back to your question. Why now? Why do they change? Why would you change from this 150-year-old technology to this now? Well, the size and the scalability drives the cost structure, but more importantly, this becomes an enablement for the future grid. And
the byproducts of that, right? I mean, the grid impacts everything from our day-to-day lives to AI data centers, which, I mean, there's such a big push right now. I mean, we're seeing data centers getting built almost on a daily basis.
Well,
right?
And that ends up being this is a lot of it is this is my belief of how this rolls out. Data center ends up driving a distributed grid out of absolute necessity. The leverage for that distributed, whether the microgrid that's powering that data center is solar based or natural gas based or wind based or whatever, or nuclear based, is immaterial at this point. It does start to become super important later on, and that's where we have a strong belief that micronuclear or small nuclear reactor deployment ends up being the face of what the future grid looks like, because now I'm deploying a grid in much smaller chunks, for lack of a better word, that aren't all so interlinked that if one piece goes down, you wipe out a whole city.
Kind of like what the fusion folks are focusing on,
exactly.
On having a localized energy capability that'll help out with, like you said, these microgrid kind of structures.
And who's the world's leader in micronuclear reactors? United States Navy. I mean, they've been driving ships around with that for a long time. So the and for us, being able to build something for that purpose puts us at the state of the art and out in front to be able to when the rest of the stuff happens, as it's data centers and then goes to factories and then goes to neighborhoods and then all the way down to emergency response. Can you imagine emergency response? The city's power goes down. You have FEMA has some micronuclear reactor sitting on back of semi trucks, and you drive that down, and I always oversimplify everything, but that's the concept, right?
It's an instant pick me up
exactly.
For that localized area, right?
Or what about rural? we were talking about where I'm from, New Mexico. There's a lot of rural areas in indigenous populations and other things where energy deployment's not quite what we all think it is living in our big cities and stuff. And so there's some huge value in all of this, and size, weight, and power are important in every aspect of that.
The industry that I think of right off the bat, I mean, this is part of the, history that I have, is the Defense Department, right? I know that you guys have been successful in engaging with DIU, the Defense Innovation Unit. Give a little background on what that looks like and why that's so important to Menlo Micro.
Well, and I kind of alluded to it just a second ago. So, and I'm going to use this to do a little validation of the technology as well as what this is for. But we entered into a proposal a couple of years ago with DIU that was looking to enable a 10 megawatt, so basically 1,000 volt, 10,000 amp advanced circuit breaker system. And I remember when that proposal came out, and a couple of guys we were talking about this thing, and it's like, well, our little 10 amp chip, how, when we start brainstorming, wait a second, this is perfect because 10 amp chips is 100 amps, and 10 of those is 1,000 amps, and 10 of those is 10,000 amps. Now, that's an oversimplification, but when you really look at how a system is built, that's really important. The second thing is you couldn't really build this kind of system with classic electromechanical devices, and the reason why is they're just too big. Right? So if I have to have all my devices be programmable versus older style, just mechanical on-off switches, is now I end up with a size and weight that's untenable for a submarine, for example. So we started looking at, well, what are you really competing
sorry
against?
to take us down this road, but you mentioned the submarine. Great example, going back to your earlier comment of the heat dissipation, right? I mean, if people are going to be sensing subs, you don't have to have this big glowing atmosphere of stuff, right?
Trailing you around the water.
I think people are going to know where the sub is. So having something like this with a small heat signature increases, the lethality of the integration of where it's going in from a defense perspective, right? So,
Absolutely. So when you look at that, then the next viable technology was transistors, because you need something small that scales and all that. So silicon carbide. So what we did was we put in our bid. There was over 100 different respondents. We don't know who the other ones were. We do know that most likely wide band gap, and this is not a dig on wide band gap, but it is showing why a conductor in some in some systems is more important than a semiconductor, and I'll explain that in just a second. So over 100 respondents, there was 3 chosen, and there was 3 tasks to do. Task 1, 2, and 3 were really about the design, the size, and then actually building a 100 amp 500 volt prototype board, which then DIU and actually the Navy tested for reliability and all of that, and performance. After that, those first 3 tasks, we were the only one left. And the reason really is that we have a little demonstration we actually do at shows where we load up a card with advanced silicon carbide devices, 6 milliohm devices, and I think on a 40 by 50 millimeter card, I think it was 8 or 12 of them. I can't remember. Well, we can put about 24 of our devices on the same. So because the power density is higher, but when you run a transistor up in temperature, its its on resistance continues to grow, and so you actually end up, now I raise the temperature, my contact resistance goes, or my on resistance goes up. Oh, that creates more waste heat. Now it goes up again, and so you actually can end up in a thermal runaway situation if you don't have really strong thermal designs. Well, in our case, the contact resistance is the contact resistance, and so as the temperature rises or the current goes up, our contact resistance doesn't go up with any temperature rise. And so we can, out of that same size board, we can get somewhere in 2 to 3 times more current or more power through that size of a board. And that's indicative of how the end system comes together. Now, why I said this is not a dig on wide bandgap, because wide bandgap has a huge advantage over us.
Of course, it has its own utility, right?
Yeah. You're trying to make a converter. I have to be able to switch an infinite number of times. There's no way that my device is going to last an infinite number of times. It'll last, 3 billion cycles, which is far longer than the lifetime of that circuit breaker system, but not an infinite number of times. I can't switch in a nanosecond. If I'm making a converter or something like that, which is just as important in all of these systems, and that goes all the way back to this comment I made earlier, where GE had parallel complementary paths for silicon carbide and for MEMS.
Yeah, I think of it just like any other tool that you would have out there, right? I mean, let's use a very simplistic model. I could go out and dig a ditch with a shovel, right? Or I could go and rent a ditch witch. I mean, one's going to have a better utility and get the job done a lot faster or a little bit more efficiently. Both will do it, but if I'm going to pick on a hot summer day here in California, I'm going to pick the ditch witch so I can get it in and out and I can have a...
Because your on resistance is going to go up with temperature.
Exactly. So, and it's interesting with the DIU piece because it's very different than a DARPA program. A DARPA program is this moonshot, hey, we hope that we can get something that is relevant at the end of this. We'll invest a bunch of money, but we don't really have a mature enough technology, when these solicitations go in. With DIU, they're saying, okay, no, we're not looking for just ideas. We're looking for something that has a utility. So that way we can start integrating for applications.
So here's what's really interesting for us. One is we're going to be a huge enabler for the Navy through this, and ultimately the DoD. However, DIU also has part of its mantra or mission is dual use. This has enabled us to validate. So here we have a 100 amp, 500 volt board that's pretty much smaller than anything else that you could build right now, and it hasn't been optimized. That's a prototype, so there's more work to complete. But when you start thinking about what that means, and we've demonstrated it. We demonstrated it at APEC not too long ago, and showed 100 amps pumping through this thing. The temperature rise above room was about 25 degrees, and no heat sinking, no real thermal design, and so what that's done is it's started to really validate the technology for us on the power side of things. I think we had strong validation on RF and millimeter wave already, but on the power side of things, and it's drawing partnerships into this thing where, we're obviously not going to be the one building the 10 megawatt system. We're going to build the chip. We're going to build the next level of board design, but the system is going to be built by partners, and it's drawing partners.
Yeah,
because it validates it.
Well, and speaking of partners, I mean, you guys aren't just a one-trick pony, right? Like, you're not just working defense-related stuff, though very valuable. The dual-use aspect has been really interesting. I know that there's been a number of pretty influential partnerships that you guys have been able to engage in that are outside of the Defense Department. If you want to talk about a little bit about that, that'd be interesting.
So actually, power is our third leg, if you will. Commercial power energy distribution's our third leg. Where our early revenue has actually started is around high-speed RF millimeter wave devices. Now, interesting to me is, and I never quite expected this, we knew we would get into semiconductor test and measurement. How important it was when we first started, didn't dream of that. We were dreaming of these other things, so kind of fast forward to now. We early on we got a design in at a I'll call it a large cell phone APU supplier. Testing high-speed serial bus interfaces, so the PCIe Gen 6 kinds of things. So that's turned into a huge niche for us. So when you start looking at where's Menlo going, well, the first place is AI. Second place is aerospace and defense, and the third place is energy. And so all three of those are critical infrastructure.
And it's interesting because you see the emphasis coming out right now from not only commercial investments, but even in the White House on all three of those sectors.
Exactly.
And these are pillars, not only within the United States, but you're seeing a reflection of this around the world. And partnering with the companies like you're just describing here, who have an exponential growth, relying on Menlo Micro to be able to help them continue that trajectory, is something that is an extremely, exciting partnership, right?
Well, yeah, and if you look at the top 25 semiconductor companies, almost all of them have a high-performance computing somewhere between a GPU and an MCU, right? Every single one of those have high-speed serial bus interfaces. We're already engaged with, I believe, 14 of them. We have 2 or 3 that are in high-volume production. We have 3 or 4 that are following on with production starting towards the end of this year, going into next year, and another 3 or 4 that will be in production sometime next year. So that's moving really quickly for us, and we are critical to that supply chain. We had to come up with the full stack, and so that became important. Well, as a real small company, raising the funds, or actually at the very beginning at Series A, raising the funds to create a factory, especially when we started 8 years ago, that wasn't in the cards. And people, semiconductors were not quite the belle of the ball that they are now, but and people hadn't been looking at putting that kind of capital into these things.
Well, and it's always been a risk-adverse technology, right?
Exactly.
Investors are very hesitant to put a single dollar into any kind of semiconductor hardware.
It's a risk. It's a big risk deal, right?
Yep.
Especially a new material science, especially on a whole new product technology that's not proving. Luckily, because of the Schenectady fab that GE had, we were able to start some low-level stuff, and GE actually took some of these to production. There was about 100,000 of them put in the field in MRI machines, basically driving big coils, right? So for MRI, so we got to prove the concept. We got to have real product in the field in I'll call it a research fab. I will give anybody thinking about this again, think twice before you decide to try to start real production in a research fab because they aren't built for that. And early on, I think there was a water leak on the second floor that contaminated half the equipment, so that put production out of whack. It forced us then to go find a commercial fab faster. And if you're in the MEMS world, real quickly, there's only 2 or 3 viable places that aren't vertically integrated with another with a semiconductor company that you can build this stuff. A couple of the normal foundries will dabble in MEMS, but only so far as it's CMOS compatible. So if you're making a metal contact switch that has gold in it on glass.
Well, now you've got messy material.
Messy material. It's not going in a CMOS fab, and so that really narrowed things down. We aren't the first company that's tried to do this. There was 20 others that did 20 years ago. They virtually all failed because you really need a new material science to do this, and so that's our secret sauce. So our desire to reshore, if you will, the technology has been there for several years. We have committed to a small fab in New York. We're slowly pulling that together and trying to be fiscally responsible at the same time. This is a tough nut for even though our revenue is growing, we're having a lot of success in a lot of areas. It's a tough nut for a small company to put that kind of capital work by itself. We are still having discussions with various partners as well to get this get this reshored. I will add something. We've had a number of different applications and stuff with the government. The hard part here is, we talked about this earlier, the specialty fab gets forgotten really easily. Maybe by no fault of any of the departments we've worked with. We've gotten pretty strong accolades from the DoD. I think you were aware that Heidi Shue, and when she was running R&E, that was a pretty strong endorsement.
As the Undersecretary of Defense for Research and Engineering, having her not only aware of your company, but a personal visit where she spent an entire day, walking around and looking at, A, why is this important? B, how is this applicable to the Defense Department? And C, how can I go ahead and educate my team on the defense side over in the Pentagon to understand why we need to have a broader spectrum of understanding? Because one of the things that the Pentagon has been very focused on is logic, right? That has been one of the areas that they have been highly focused on, and for a variety of reasons.
All the right reasons. Absolutely.
But we all understand that in order for the Defense Department to operate, it takes a high mix of technologies at low volumes. That is the model in which the Defense Department operates. And that includes, technologies like Menlo Micro creates, and having an understanding of why that is important. I mean, just the submarine example is a primary reason why there should be attention focused on this. Having a bunch of people that are submerged in a ship, knowing that they have this big beaming light of, hey, adversary, come shoot me. I mean, that is a horrible thing to think about.
Well, and we've got another product going into production pretty soon that's going to be in, I hesitate to say all, but a majority of guided munitions in the future, because it protects the radio front end. Well, what's the most important part of a guided munition is the part that guides it.
The nose, yeah. It's
and so that protection from jamming energy, whether it's self jamming or enemy jamming, is really key. Well, we provide a way to do that. That's not that is a huge disruption, I guess I'll say, in the way that's done today.
Now, this business model within the Defense Department is actually a very different one. I talked about high mix, low volume. Usually it's long sustainment that goes from there. But from a munition perspective, I mean, there's a reason that Raytheon has, cut loose a lot of their marketing department, because they don't need to sell their missiles anymore. They're just getting used on a regular basis for all the conflicts the United States is helping to, support around the world. So
I'll give you another quote I learned from Jim Peterson at Microsemi. Unfortunately, peace is not close at hand. So it's this necessary evil thing, but we want to be able to be part of the security of the country and security of our allies. So.
It's a reality of the situation the world is, right? I mean, not everyone plays nice, and if you're not ready to understand the reality, then I mean, you're the next one on the docket, right? It's now you've talked about a lot about where you're at today and such. I mean, with the technology, there's been a number of recent accolades that you guys have received, in highlighting, how important the work that Menlo is doing, right? Do you want to talk a little bit about that?
Yeah, I'll talk. Here. I don't know where I should point this. What's cool about this award? There's two really cool things about this award. One is it's called the Thomas A. Edison Award for Semiconductor Innovation for AI. So here we're making a mechanical switch, and we won the award for Semiconductor Innovation for AI, which is really interesting. First cool thing is it's the Thomas A. Edison Award, which that's our heritage.
Connected dots right there. Yeah.
Exactly. I told you the story at the beginning here. The second piece of this is when we won this award, guess who the kind of the star of that show was? The star of that show was NVIDIA. Jensen Huang was there to accept an NVIDIA award. And so for us to be honored at an innovation award that's named after our forefather, if you will, about AI, in conjunction with the leader in AI and GPUs, was quite a cool accomplishment for us.
I don't think I've seen it. Can I
it's cool. It's got the light bulb, right? So it's
that is pretty neat. Yeah, just right here in 2025. This is for high-speed differential switch. I mean,
yeah, our CFO Mark Sheffield
cool.
went to Florida to accept the award, and he got a cool, fun picture with Jensen, so that was kind of neat.
So what's next for Menlo? You guys have created a capability that is starting to integrate into a number of different things, everything from defense-related applications. We talked about how it's going to be helping the energy grid and the pillars associated with the company. I mean, even as recent as this AI award, which is yet another differentiator on how important your technology is influencing a specific sector. How do you see things growing for Menlo?
So to start out, the next couple of years, what I think what people will be able to see, and what we expect to be able to do, is kind of sustain growth, and it's going to leverage off of this AI sector, test and measurement for high performance computing. And that's going to continue to grow. That's just starting out, and I think the revenues will continue to be really strong from there. On top of that, I mentioned some of the aerospace and defense things that are starting to move into production. So that'll layer on top of that. Those two things, and there's a few other applications around it, but those are two primary applications that are based on our high frequency products. And if you look again at this banner back here, the one on top is it's basically a 20 gigahertz, 25 watt a single pole 4-throw switch. And the engineers out there will think of the hundreds of things that you can do with that switch, but that ends up being the bread and butter. And there's a roadmap associated with advancing that even further up to 50, 60 gigahertz. The chip on the bottom is the power chip. So that's a 10 amp 400 volt device. And so what you'll see on the power side is, over the next couple of years, a lot of focus on what we're doing with DIU and associated partners there to develop the power applications and get those productized and ready for market. So really, I'll say material revenue coming from that stuff is really, 24, 36 months away from now. And so, but that ends up being the third leg. As you start scaling this thing, the ability to drive a cost structure here. So this is a far simpler manufacturing. It's got a lot of nuances to it because of the chemistry to create the alloy. But after that, the fundamental complexity, I guess, of the manufacturing process is maybe 25% of SOI. And so, and we're not using any fancy lithography. Remember, I said we're making so we need accurate lithography, but it doesn't have to be fine lithography. And so we're making 50 micron devices. So the ability to scale this thing to very low cost structures is really high. And so subsequently, every quarter we have an all hands meeting. I tell everybody in the all hands meeting, 5 to 10 years, everybody will have touched or affected by some application that the Ideal Switch is in. And the long-term vision. Okay, where do you go from circuit breakers? Well, I go to contactors. I go to relays. I go to e-fuses. I go to programmable light switches, right? And if you and the original premise of this thing is that if you couldn't make a programmable light switch for the same cost as what I can go buy one that I can turn on and off for at Home Depot, 10, 15 years ago, then we missed the mark. And now I'm not saying that light switches is the goal here, but what it is it's a measure, right, of how well a technology is able to to permeate every application that you can think of putting a switch in.
But companies have made a killing in the light industry, right? Look at Cree, right? I mean, a great example of transitioning from the LED, from the fluorescent bulb. I mean, there is a humongous market there, and knowing that there's such a differentiated spectrum of integration opportunities is phenomenal. I mean,
if you can make a consumer level a circuit breaker, you can make a consumer level light switch, right?
Exactly.
And by the way, if you can do that, you can make very low cost antenna switches. You can make very low. There's a number of applications that you can shift dramatically by having you can make a very low cost beamformer on a satellite, for example. So that's all of that comes into play as these applications migrate into a greater and greater need for scale, a greater and greater need for the performance we provide, but at a cost point that makes sense to replace the old technology.
Well, Russ, I'm very excited to see what the future here at Menlo is going to be, and I really appreciate you spending the time here on Micro Journeys. Thanks a bunch for taking the time.
Thanks for having me. This was fun.